Hello everyone and welcome back to NPTEL course in Pharmacognosy and Phytochemistry. We are doing week 10 in which we are seeing different quality control methods for evaluation of herbal drugs. So far we have covered microscopic methods, macroscopic methods, organoleptic methods and physical methods of analysis of quality control. Now today we are going to dwell into a different set, that is your chemical methods of quality control. Now chemical methods of quality control, as we previously saw, can be broadly divided into two categories. The qualitative method. The qualitative methods are the methods which will tell us if the compounds, especially the phytochemicals or the chemicals which are representative of the plant, are present or not in the given sample. Now this sample can be a plant material, this sample can be a plant extract, or this sample can be a herbal formulation. When we do this, we can just say that if the compound, that is especially a flavonoid compound or a triterpenoidal compound, is present or not. This, recollecting our chapter tannins where you saw these three test tubes, if you recollect, this was your ferric chloride test. And what we said is, when your tannin extract, if you treat it with ferric chloride and your color of the solution changes to green, we say that they are condensed tannins. But if the color of the solution changes to blue, we say they are hydrolyzable tannins. So through this test, we are sure that our extract contains tannins. Through this test, we are sure what type of tannins are present. So qualitative will give us that kind of data. Similarly, another example where you can do a qualitative test is just a thin layer chromatography. Here you can see that you can just mark a standard compound or a set of standard compounds and just check at the same RF are the compounds corresponding in the extract. So if the corresponding band is always seen in the extract, we can be sure that our marker compound is present. So is it present, is it not, and what type of compound is present is what you can get from the qualitative analysis. Now coming to quantitative analysis, in this if you specifically see, here you are going to quantify. That means how much of this compounds are present. So if you see this graph, maybe in UV, there is something we call it as absorbance value. So more the compound present, probably higher is going to be a absorbance value. Whereas if you see your HPLC, again the place or the position of the peak will tell you whether the compound is there or not. But if you see this peak, the area under curve of this peak will tell us how much quantity of the compound is going to be present. So chemical methods of evaluation are much more accurate. They give us what type of compounds are present, they tell us how much the compound is present. So let's see different chemical methods of evaluation. So when we are seeing or when we are discussing our methods of evaluation today, we are going to discuss qualitative method. That is, qualitative method includes phytochemical test or identification test. It includes microchemical test or histochemical test, which is done under microscope. This might also include your limit test for heavy metals. See, whenever you are processing a herb, there are impurities which might come in, and some of these impurities include your heavy metals. The heavy metal poisoning causes a lot of acute disorders, and as a result, the limit to the amount of heavy metal that should be there in the sample has been specified by different pharmacopoeias. So we will be seeing limit tests as well as we will be seeing TLC as a method. So in this particular session, we will be seeing phytochemical evaluation, microchemical test, limit test as well as thin layer chromatography. In the subsequent sessions, we will also be discussing a few quantitative tests, including quantitative tests for different classes of phytochemicals, specific determination of compounds using chromatographic techniques such as your HPLC, HPTLC, UPLC, gas chromatography, Then we will be analyzing our pesticidal residues, determining mucotoxins such as aflatoxins, and during the process of extraction, we use solvents. Are there any residual solvents remaining in our sample? This will be discussing in the subsequent session. So now, seeing in depth of qualitative method of analysis, let's start with phytochemical methods. So, phytochemical methods, as I can say, summarizes the previous 9 weeks that we have discussed. So, in the 9 weeks that we discussed, we discussed different set of phytochemicals. We saw their properties, but at the same time we saw their chemical properties. What does it mean? We saw their chemical reactions, what is the shape or what is the structure of the compound, and specifically what does compound react with, what colored reactions do they produce, and those are called as your phytochemical tests. So, every chapter gave you little idea about the evaluation of those class of compounds by their phytochemical tests. So, let's quickly summarize them here. So, if you recollect in the flavonoids, when you have your benzogamma pyrrone or more specifically phenyl benzogamma pyrrone nuclease, it answered to what is called as Shinoda test. Do you recollect what it is? It is basically a test which was used to reduce the flavonoid nuclease, and this was done using magnesium turnings and concentrated HCl, which reduced the flavonoids to anthocyanins, giving you a cherry red coloration in the concentrated or pure form and a slight orange pink coloration if it is in the extract form. Similarly, whenever they were treated with alkali, you got what is called as alkaline reagent test, which gave a nice vivid yellow coloration with flavonoids. Now, similarly, recollecting your unit 4, that is your tannins, if you remember, tannins have the ability to tan the skin, and in this test, or particularly in this gold beaters test, we checked its ability to tan the ox intestine. Similarly, the ability of tannins to precipitate proteins were also evaluated by gelatin test. Then maybe in your unit 5 or week 5, we saw alkaloids, and alkaloids, because of their nitrogen content, gave you a positive Dragendorf test, which was potassium bismuth iodide reagent, and gave you a orange color precipitate, whereas with Mayer's test, which is potassium mercuric iodide, you got a whitish color precipitate. Similarly, when you see anthraquinones drug, can you all recollect? We did 2 anthraquinone containing drugs, specifically your aloes as well as your senna. At the same time, we also saw a colorant called as cochineal. So, all of these anthraquinones follow a test called as Bontrager's test, which in presence of alkaline pH, your free anthraquinones gave you a pink or a cherry pink coloration. This was true, that is the Bontrager's test is true for O glycosides, but when you want free anthraquinones from C glycosides, so that is when you want your free anthraquinones from your C glycosides, what you do in this case, you use little harsher reagent, and that harsh reagent was your ferric chloride. So, you are going to take ferric chloride and hydrochloric acid, you are going to hydrolyze the C glycoside and then kind of partition in chloroform, and then you kind of made it alkaline either by caustic alkalis or by ammonia. That test was your modified Bontrager's test. Similarly, for your coumarins, they have their inherent ability to produce fluorescence, and this fluorescence can be seen more enhanced in alkaline and in some cases even in acidic pH. So, you saw fluorescence test for your coumarins. Volatile oils, we saw non-specifically you pour volatile oil on any filter paper, it will evaporate. So, initially it will stain, and that stain will be transient because the oil is evaporating. At the same time, because of the terpenaceous content, it gives what is called as your vanillin sulfuric acid test. So, when your volatile oil containing chloroform extract is treated with vanillin sulfuric acid reagent, in that case you get a red to reddish brown coloration. Not only that, we also discussed steroids and triterpenoidal compounds Do you all recollect this test? This test is more specifically called as your Lieberman-Burkhardt test, in which you took a anhydrous chloroform extract of your drug, and in that you carefully added acetic anhydride and slowly a small quantity of concentrated sulfuric acid. What happens is you get a greenish coloration. Similarly, you did a Salkowski test but without the acetic anhydride. And the simple tests were your foam test for saponins, where you just had to take the aqueous extract and shake it well. It generates a copious foam which is stable even after 15 minutes. Similarly, saponins have the ability to hemolyze the RBCs, and this hemolysis test forms the evaluation of your saponins. So, if you are given a drug, or if you are given a herbal formulation, or you are given a herbal extract, now what we have done so far is we have discussed drugs category wise. So, when we said orange peel, we discussed flavonoids. We didn't discuss pectin, we didn't discuss essential oil. But if you take this orange peel and do the phytochemical test, there is a good chance that you will get your essential oil test positive, because orange contains volatile oil. It will give you test for your pectin positive. It will give you your test for flavonoids positive. Similarly, if you take your licorice as a drug, licorice contains flavonoids, licorice contains tannins, licorice contains even your saponins. So, a herbal drug, depending upon what all constituent it contains, will give you a set of test positive. So, this is what you call it as phytochemical evaluation. So, whenever you are given a new drug to assess, you carry out this series of tests and check what all phytoconstituents are present. Then you check with literature, are they corresponding to that? If you see that in your tannin containing drugs, say for example nut galls, your tannins test, that is your Goldbeater's test, is negative. What does that mean? Either that gall sample has been exhausted, that means the tannins of it has already been removed, or it is a sample other than nut gall. So, there is a good chance of adulteration or substitution happening there. Now, in certain cases, it is not a class of phytoconstituent that is detected. Sometimes you check for specific phytochemicals. So, say for example, I want to check whether the sesame oil or sesame oil which is given to me is genuine or not. In that case, I will do my Bowdoin's test, which is more specific for sesame oil, rather than doing a test for lipids. If you remember, your test for lipids was your saponification test. That is not going to tell me whether it is a sesame oil or it is a castor oil. Sometimes I need to be more specific and I need to move drug wise. So, some drugs answer some specific tests. So, that specific test will help me in ascertaining whether the sample given to me is genuine or not. Here are a few examples. So, sesame oil gives you your Bowdoin's test. If you recollect, in this what is done is you take a little bit of sucrose and react it with hydrochloric acid, shake it for a while, keep it for 5 minutes, and you should get a reddish coloration. Similarly, if you recollect aloes, now anthracquinone's test will be given by aloes, it will be given by senna, it will be given by most of the drugs containing anthraquinone. So, Bontrager's test is going to be non-specific. If I have to specifically check if the sample given to me is aloes or not, what I can do is I can do a borax test. So, if you recollect, borax test was a test in which aloes was initially boiled in water, filtered, and to that filtrate little bit of borax was added and heated. So, later on when you put this solution under UV, you got a greenish color fluorescence. Now, this test is not going to be answered by all anthraquinones. So, this is more specific test for aloes. Remember, we also did a fluorescence test for Asafoetida, but this time the fluorescence was blue in color. So, Asafoetida contains umbellic acid, and you could convert it into umbelliferone first by hydrolyzing the ester and then cyclizing it. So, initially you treat it with hydrochloric acid and later on treat it with ammonia to get a nice blue color fluorescence. Now, not all your oleogum resins will give you your fluorescence test, but definitely all oleogum resins will give you an emulsification test. So, emulsification test will tell me it's a oleogum resin, but your fluorescence test will tell me specifically if it is asafoetida or not. Giving you few more examples from the carbohydrates. When we did acacia, we said acacia contains an enzyme, especially the fresh sample, called as peroxidase. So, if you take this and if you take little bit of benzidine and hydrogen peroxide, this peroxidase enzyme will help in oxidizing it and your benzidine will form a blue color compound. So, the presence of blue coloration will indicate it's acacia when I compare, or if I am doubting whether the sample given to me is acacia or is it going to be tragacanth. Maybe in some cases I have mixed sample up. So, there is going to be tragacanth and I am not sure what it is. Rather than doing the test for gums, I will carry out more specific test for acacia. Now, another specific test is your Vitalimaurin test, which is true for tropane alkaloids, especially if you see your atropine. So, in this case, you are going to extract your alkaloids in a suitable solvent and dry it. And to that dry residue, you initially treat it with nitric acid and later on with the potassium hydroxide to get a purplish color coloration or a residue. Now, the last example I am giving in this case is colophony. So, colophony again is an example of resin. Now, resins again are non-specific. So, I know colophony contains abatic acid. So, making that abatic acid react with copper acetate or cupric acetate more specifically. So, what will it do? It will convert that cupric acetate to a nice emerald green coloration. That will help me ascertain that it's colophony and not plastic masses. So, previously in the previous slide, what we saw here is, here you have classes of compounds. So, I can take a polyherbal formulation, I can take a herb, I can take a sample and evaluate whether this class of compounds are present or not. Whereas, if I see the subsequent slide, in this slide the specific tests tell me that whether this herb particularly is present, whether this phytoconstituent is particularly present in the plant or not. So, in some cases where the drug is exhausted, you will predominantly know if the compound is there or not using specific phytochemical tests. In some cases, what is done is the chemical test will tell you if the impurities are present. So, forget the classes of compounds, forget the compounds. What if you can specifically check if some impurities are there? I will give you an example. Say for example, when we discuss lipids, we said lipids are esters of fatty acids. Now compare that to paraffin. Paraffin is just hydrocarbon. Now when you do an saponification test, your fatty acids will saponify, whether your paraffin will not saponify. So a saponification test will tell me whether it is a triglyceride or a fat or a wax, or is it really paraffin that is not saponifying at all. On saponification, your soap will dissolve in water, but paraffin cannot dissolve in water because it will not saponify. Similarly, some cases what happens is your acacia, agar, they are little expensive. So, people often tend to dilute them with starch because starch is very cheap and easily available. So, you know that acacia and agar do not give you blue coloration with iodine, but starch does. So, when you take your acacia or agar sample and you treat it with your iodine, especially your iodine solution, that is iodine and potassium iodide, if they are showing you blue coloration, that means there is a good chance that your acacia or agar have been adulterated with your starches. Similarly, cottonseed oil is a very cheap oil and it's not considered to be good or properly edible also. So, in some cases this being a cheap oil is often used as an adulterant for other oils. So, I can easily check. What I need to do is I need to dissolve that oil in carbon disulfide and then add little bit of sulfur in amyl alcohol. If I am getting a reddish coloration, that means that sample of your fixed oil contains what is called as your cottonseed oil. We also saw adulteration of honey, and in that case we checked what is called as Fees test. So Fees test is basically a test where you can check the quantity or amount of hydroxymethyl furfural. Now this hydroxymethyl furfural is naturally there in your honey, but it is present in a very minute quantity. But when you are dealing with synthetic invert sugars, the quantity of hydroxymethyl furfural goes very much high. So in that case, if I just take this honey and treat it or extract it with ether, and this ethereal layer, if I treat it with resorcinol and hydrochloric acid, if I am getting a reddish coloration, which is a persistent thing, in that case I say that my Fees test is positive. That means my honey is adulterated with an artificial invert syrup. Similarly, in some cases you will find that there are natural medicines, or people claim that those are natural medicines, and then they add certain steroids to it for getting enhanced effect. What I can do in this case is to check for those steroids. Now mind you, in some cases what will happen is the plant may also contain some natural steroids. Those cannot be evaluated if the plant material is containing steroid. But if the plant material is not a rich source of steroids and contains steroidal compounds in a very minuscule amount, so that they give this test almost negative. In that case, suppose with the formulation you are getting this test positive, that means it indicates that your given preparation is containing steroids. Now this can be evaluated by the same test, that is your Lieberman-Bouchard as well as the Salkowski test. Now moving on to the next set of evaluation tests. Now this set of evaluation tests uses microscope. Now imagine chemical test done under microscope, or chemical test done in a quantity is so minuscule that you will have to use a microscope. Yes, and this happens when you use something called as microchemical or histochemical tests. Now microchemical or histochemical tests are as simple as adding a iodine on a section. So when you do a transverse section, if you add your iodine, you know your iodine is going to stain your starch. So you can see here, this is a turmeric sample transverse section. So when I carry out the transverse section of this rhizome, I mounted, it's going to be colorless with some yellow specks, and this yellow specks resemble curcuminoids. Now if I have to check the presence of starch, you can see some blue specks here. What I have done is I have just added iodine. So if a drug naturally contains iodine and it turns blue, that is good because it's a genuine drug. But if a drug naturally does not contain iodine and still stains blue, that means some other plant part has been added to it. Similarly, we saw that there are certain plants which contains mucilage. A good example of that is isabgol. You can check whether it is genuine isabgol or not by staining it with ruthenium red and seeing under microscope. So if it is genuine mucilage which is swelling, it will acquire a reddish coloration with the ruthenium red. But in some cases, you know, if it is swelling or if it is forming a slimy consistency because of carbohydrates which are not mucilaginous, say for example gums, in that case you will not get your red coloration. Similarly, you can check for the presence of lipids, that is the occurrence of fats, waxes or even oils, more specifically your fixed oils and volatile oils, by staining with a lipophilic stain. Now this lipophilic stain are your Sudan red and tincture alkana. So they have good affinity for lipids. So what is going to happen? Because of their affinity, your lipid is going to absorb that stain. So your whole section will be colorless, but wherever the lipids are present, you will get a nice pink to reddish coloration, whether you use your Sudan red or your tincture alkana. Now not only that, you might have seen that in certain transverse section, say for example Rauwolfia that we discussed previously, just addition of nitric acid and seeing that coloration will tell us that Rauwolfia contains reserpine or not. Is it there or is it an exhausted drug? Now similarly you can do it for alkana. Now alkana, you know, contains your naphthazarin pigments, and this naphthazarin pigments turn blue when they are treated with an alkali. So take those alkana sections and just add a drop of your base. If the section or a part of section is turning blue, in that case you can tell that definitely it's a genuine alkana drug. Similarly for clove, clove contains volatile oil and a chief constituent of that volatile oil is eugenol. So if you have a clove thick section and you drop in your potassium hydroxide, within that oil cavities you should see your crystals of potassium eugenate. If you are not seeing it, that means the clove has been deprived of the oil. Similarly, you can also check simple features such as suberin, lignin. A good example in this section is section of ephedra, and you can see here, so this is the brownish matter which is pith, but you can see a xylem acquire slightly pink coloration with your fluoroglucinol HCl, and that indicates your xylem here is lignified, and so is your pericyclic fibers. So certain staining reagents also help me in identifying the different tests. Moving on to the next set of qualitative evaluation. Now this is not clearly qualitative, this is kind of semi-quantitative evaluation. Now semi-quantitative evaluation, I will give you an example, and that is your limit test. So whenever I want to lay a benchmark or a limit on the quantity of substance that can be used, or the pharmacopoeias use what is called as the limit test. Now this includes your limit test for chlorides and heavy metals and other substances. So let's see the limit test for heavy metals, as more and more monographs, especially the pharmacopoeial monograph of herbal drugs, specify that you should carry out the limit test for herbal drugs. Now in order to do that, what you need to do is, first thing, if you take the herbal drug, it is colored, it is maybe odd in consistency, there are drugs which are organized, there are drugs which are unorganized, and that creates a lot of problem. So the raw material whenever you want to do a limit test is the ash. So you are going to take a gram of drug substance, you are going to completely incinerate it. Now with the previous sessions, you know that once you ash it, your organic content is gone and what is left is your inorganic content. Now this inorganic content is kind of suspended or dissolved, okay, and you use what are called as Nessler's cylinder because we want comparison. So in this case, say for example, when I am doing the test or the limit test for heavy metals, what do I do is I use a standard lead solution to compare, and this standard lead solution is about 20 ppm. So the solution should not exceed 20 ppm per ml of lead. Now I will take my ash, this ash also I will keep it, and I want the same thing. So how do I do this? I will use my standard lead solution, I will use my sample ash. Now in both cases I will treat them with H2S gas. Now H2S gas, how do you do is you create a H2S solution by bubbling H2S gas through the water and then you pour in it. Now there are different methods. If you go to see the Indian pharmacopoeia, they use H2S gas in method 1 and 2 and sodium sulphite in method 3. So pharmacopoeias also specify different methods. So what is going to happen? Say for example your lead metal is there, that will react with H2S, and what you are going to get is a PBS. Now PBS is actually a black color precipitate. So as a result, this whole solution, when I make up the volume, will appear like a blackish brown solution. Now this blackish brown solution, when I compare it with standard, now standard, because I know it already has 20 ppm, will acquire a certain brown tint. If the brown tint of my sample is darker than that, what does it mean? That means my lead concentration is higher than 20 ppm. In that case, my sample fails. But if the color of my sample is lighter than the standard 20 ppm lead, in that case I can confidently say that yes, my sample might have heavy metals, but they are below the limits. So that is how you do the limit test for metals. Another qualitative test what we have seen also previously is your thin layer chromatography. So thin layer chromatography, if you recollect, uses a very polar stationary phase, uses a very non-polar mobile phase, in this case toluene ethyl acetate, and then you spot your sample and make it run. Now in a developing chamber. Now when you run your sample in a developing chamber, as the sample passes, because of its lipophilicity, hydrophilicity, there is a pull and push and eventually it stops at a particular point. We call this as your retention factor or RF. So depending upon how polar or how non-polar it is, your extremely non-polar compounds will be seen at top, whereas extremely polar compounds will be seen at the bottom. Okay, and depending upon how polar or non-polar other compounds are, say for example, I can say of all the compounds, this is the most non-polar compound which is present in my black pepper, whereas this is the most polar compound which hasn't even run in the given mobile phase. Now I might have different visualizing agents also. The first case, the plate is just seen under UV 254. The reason is I am using a fluorescent plate, so it already has a fluorescence. So whenever an organic compound will run on it, the fluorescence is not able to reach my eye because this organic compound is quenching it. So this quenching leads to formation of black color spots. In the second case, I observe a little bit of faint coloration, and that is because this compounds produce a slight glow and a fluorescence. So under UV 365, this compounds are fluorescent. But in some cases, if I don't see the compound at all in this two wavelength, what I can use is I can use a derivatizing agent. These are the same reagents which we use for chemical tests. So remember, for black pepper it's piperine. So piperine is an alkaloid. So I am using Dragendorf reagent as a derivatizing agent, and as a result I can see instead of a orange brown precipitate, the spot where my piperine is present has become orange brown. So these are few chemical quantitative, these are few chemical qualitative tests for evaluation of herbal drugs. Here are few references if you wish to dwell more into this, and thank you everyone for your patient listening.